Hey guys, so this is chemical reaction, okay, the continuation of grade 10 review before we move into topic 1. So we're not going to spend a lot of time on it. It's not like back in grade 10 where we spent a couple of weeks on this. We're just going to spend a few days just to get yourself back into the groove by looking at chemical reactions, learning how to balance some of these chemical reactions and identifying the type of reaction. Now, so today we're going to look at synthesis. Okay, and the general formula, or the general reaction of synthesis is that when you have two reactants, now these reactants can be elements and they can be compound. Okay, but what's for sure is that these two entities are going to come together to become one. To become one, that's actually a song. To give you a compound, in this case, Z. Okay, so let's fill in the blanks here. Okay, this is from your course pack. The page number is 116, so make sure you go to 116 and put this together. Okay, so a synthesis reaction involves the direct combination of two substances to produce one new substance. In a general reaction that you see right here, where X plus Y will give you Z. X and Y can be elements or compound, but Z, it has to be a compound. Be pretty ridiculous if Z is an element, right? Well, you know what? That can happen if you're looking at stuff like nuclear fusion, but we're not looking at nuclear reaction, are we? We not even want to get to that. So that's the general idea of synthesis. Now we'll go back to this little idea later, okay? Because environmentally, there's nothing more important than this, okay? So let's take a look at the different types of synthesis reaction. I have 4 general types. There's actually more, but these 4 general types are, I guess, most general of all general types. The first one, okay, if you have a metal and reacting with oxygen gas, okay, or a non-metal reacting with oxygen gas, you form what we call oxides. Now, it could be a metal oxide, it could be a non-metal oxide. The idea here is based on what's on the reactants, right? So let's take a look at the first example. The first example we have is magnesium, which is a metal. That's pretty obvious right here. Reacting with oxygen gas to give you a metal oxide. And this metal oxide is going to be magnesium oxide. Now, it would be pretty bad if you think that Mg plus O2 gives you MgO2. That would be ridiculous. Now, don't get me wrong, MgO2 actually exists, eh? There's actually something called MgO2, but it's actually known as magnesium peroxide, but not magnesium oxide. But that's not something that I want to get into right now. It's not going to be MgO2. Cross method always apply. Always apply at all time. Why is it just MgO? It's because Mg has a natural 2 plus charge. O has a natural 2 minus charge. It doesn't matter what this is. This will matter later when we start balancing these kind of things, man. So because of that, because of the cross method, we have Mg2O2. And of course, these two are ratios. They are reducible because this is an ionic crystal. The answer is really MgO. Okay? So the answer is MgO. Due to Mg being plus 2, due to O being minus 2. Now, this is when this 2 actually comes into play. I didn't forget about him. This is called balancing chemical reaction. The main idea here is this: law of conservation of mass, meaning that the total mass or total entity of the reactants, which is this side, has to equal to the total entity of the products. Okay? Like how energy is conserved before and after reaction, mass is also conserved before and after reaction, meaning that the total number of particles here has to equal to the total number of particles here. Right now they're not. Because if you look at this, mg is fine. There's 1 mg on the left side and 1 mg on the right side. Oh, mg is great. But look at oxygen. There's 2 oxygen on the left side, but only 1 oxygen on the right. Oxygen needs to be balanced. And some people may think, just put a 2 here and gee, let's go. No, then this is not magnesium oxide anymore. You can't do that. That's ridiculous. You have to have magnesium oxide. Magnesium oxide has to be the product. You put a 2 after O, that becomes magnesium peroxide, and that's not legit. That's wrong. The only place that you're going to put a 2 is in front of the chemical formula, because this right here actually means 2 magnesium oxide. You didn't change the chemical here. It's still magnesium oxide. By putting a 2 here, you're saying that there's 2 of these magnesium oxide. 2 moles to be exact. Okay? Now, think of this. Now oxygen is balanced. There's 2 oxygen on the right side, 2 oxygen on the left side, but, oh my goodness. Before, magnesium was balanced, but right now magnesium is no longer balanced. By putting a 2 here, we're saying that there's going to be 2 magnesium. Well, it's not hard to fix that, right? To fix this, just put a 2 here. Okay? So when I kind of lay this out, you have Mg, 2 Mgs, you have an O2, okay? Which is great. No. 2 Mg on the left, 2 Mg on the right. 2 O's on the left, 2 O's on the right. Okay? Now this comes with a lot of practice. The more practice you do, the better you get. That's just the way it is. All right. The next example is a non-metal oxide example. So you have a non-metal like carbon. Okay? Reacting with oxygen gas will give you a non-metal oxide. Now, normally at the right pressure, at the right temperature, you should get carbon dioxide. But there are chances where you might get carbon monoxide. So what that means is that non-metal oxides is a little bit harder to predict than metal oxide, because you don't use no cross rule to make determination of what product you're going to get. So at some odd times, you might just have to memorize these things. This is one that you may want to memorize. Let's put a star here. And make sure you balance it. The good thing is it's already balanced. How sick is that? All right. The next question is something that, of course, you can easily predict, because aluminum is a metal and all metal has a charge. And for this one, you're looking at ALO, but not just Al1O1. You need to recognize that Al has a natural 3+ charge, so you better put a 3 here. O has a natural -2 charge, so you better put a 2 here due to cross rule. Okay, let's balance. Let's balance. Looks like there's 1 Al on the left and 2 Al on the right. Okay, for now I'm going to put 2 here just to satisfy the fact that the aluminum is balanced. for now, oxygen needs to be balanced now. There's 2 oxygen on the left and 3 oxygen on the right. Okay, well, common multiple for oxygen is 6. Common multiple. People get scared when they hear that. To get 6 oxygen on the left, you need to have 3 oxygen gas. There you go. 3 times 2 is 6. Which means I'm going to put a 2 here on the right because 3 times 2 is 6. Oxygen is fine now. But just like how happened earlier, for me put a 2 here, I messed up the balancing of aluminum because right now on the right side, aluminum is 4. That's not a big deal. All I have to do is change this number to a 4 and everybody's happy again. All right. So, oxides, not a big problem. Not a big problem at all. However, what happened if I give you something like this? Iron plus oxygen gas. What are you going to get? Now, this is a trick question. Okay? You need to ask yourself when you're doing your product. It's going to be some sort of iron oxide. But then iron has multiple charge, man. Iron can be +2 or +3. So, which one am I going to use? Well, they will both exist. Okay, if you were to do this reaction, iron reacting with oxygen, both products can exist. So let's say it's the +2 iron that we're looking at. The answer will be FeO. Okay? The answer will be FeO. Which means if I'm going to balance it, I better put a 2 here and put a 2 here. There you go. Everybody's happy. Now, to actually get full marks on this question, you have to have a separate reaction where Fe plus oxygen gas can also give you this combination, Fe2O3. This is based on the fact that this Fe is a 3 plus Fe. Now people are maybe asking, can I just do this? Can I just do this? FeO plus Fe2O3? Can I do that? The answer is no, you cannot do that. In fact, if you do that, you'll see you have a hard time balancing this. Well, this one is not that hard to balance. Okay, it's actually pretty easy to balance, but this is not right. This is not true. Because iron plus oxygen gas don't give you a combination of these. At least not one reaction. It's a separate reaction. Okay? The fact that +2 iron or +3 iron is reacting with oxygen gas is all based on random. Okay? So what you need to do is put both of these reactions as a reaction of existence. And you will balance them independently. Like what I just did right here. So make sure you keep that in mind. That's extremely, extremely important. All right, let's move on to the second type of synthesis. Okay, type B, where you have metal reacting with non-metal to give you some sort of binary compound we call salt. Again, Ross rule applies, right? So in this case, it'll be CaCl2 because Ca is +2, Cl is -1. And cross them, this is what you get. Hey, I love these. You don't have to balance it. For lazy people like me, we love it. K plus S, well, that's K2S. Okay, let's put a 2 here for the sake of balancing. Why K2S? Very simple. K has a natural +1 charge. S has a natural -2 charge. Cross them, you get K2S. Okay. Again, you want to be careful if you have metals being multiple charges. Then you have more than one equation that are involved. Okay. All right. Well, let me just give you an example. Why not? Why not? Copper plus nitrogen. Okay, what are you going to get? Well, if it's a copper, it can be +1 or +2. Let's say +1, you'll have Cu3n. This is based on copper +1. Or you have copper +2, which will be Cu3n2. Okay? Again, you balance them independently, like that, and like that. Sick, huh? All right, let's continue. Oh, this is great. Metal oxide reacting with water. So back when we were doing part A, we made a couple of metal oxides. These are also metal oxides. If you take these metal oxide and you put it in water, what you'll get is something called a base. Now, we all know what bases are. Bases are metal hydroxides. Okay? And that's pretty obvious in this case what metal hydroxide you're going to get, because the only metal you see in town is magnesium. You don't see any other metal, do you? I hope you don't. So magnesium oxide reacting with water will give you a metal hydroxide, and the metal hydroxide is going to be magnesium hydroxide. Again, cross rule applied. The hydroxide has a natural charge of -1. This is +2. That's why we have Mg bracket OH2. Okay. Oh, it is already balanced. Love it when that happens. So, if I have FeO plus water, what am I going to get here? Well, remember, in this case, charges is always consistent. Okay, you always have to keep charge consistent. This right here is a 2 plus Fe. So what that means is that the product will still have to be a 2 plus Fe. You're not going to change to a +3 Fe, are you? How did that happen? Why would it change? Naturally, I have a charge of +2. That's why I'm FeO and not Fe2O3. I'm going to remain 2 plus. I don't change. So this will be FeOH2. Okay? And not FeOH3. Again, something to keep in mind. All right, lastly, I have these non-metal oxide. Okay, like carbon dioxide, or maybe even sulfur trioxide, or maybe even nitrogen dioxide. These are all non-metal oxides. Okay, so they are missing a word here. Non-metal oxide. If you put non-metal oxides together, you're going to get an acid. In many cases, it's going to be an oxyacids, which we have already talked about. Okay, so these are a little harder to predict too. Okay, because there are different variation of oxyacids, especially when you decided to play with the number of oxygen atom. So again, some of these things may have to be memorized, like this one. Carbon dioxide reacting with water will give you carbonic acid. Okay? Carbonic acid. So, again, make sure you kind of have a good understanding of the general reaction for all four of these types. Okay, for metals or non-metal reacting with the oxygen, you'll get metal oxides or non-metal oxides respectively. Metal plus a non-metal gets a binary compound. When you take these metal oxides right here and you put it in water, you're going to get a base. If you put a non-metal oxide in water, you're going to get an acid, like this. Now, before I call it a day, I guess I have two. I see one here, but if I really have another one that I want to show you. I want to look at some environmental factors based on, of course, this synthesis reaction. Okay, to make it more real. So let's go right here in the beginning. This is a very, very important stepwise reaction, because this reaction occurs right after another, meaning that you start with S. You actually don't start with S. Yeah, you know what? You actually start with S8. Put an 8 there. This is octasulfur. This is what really exists. Elemental sulfur is quite rare. Sulfur, being sulfur as is, usually is in the form of S8. So maybe put an 8 here. Okay? By doing that, you might want to put an 8 here too, because these has to be balanced. While you're at it, you might as well put an 8 here as well. Okay? So, sulfur reacting with oxygen gives you sulfur dioxide. Okay? Now, this sulfur dioxide will react with more oxygen to give you sulfur trioxide. As I said, this is a stepwise reaction, meaning that this product very quickly will react with more oxygen to create this product. Whereas this product, very light, will most likely float up into the sky to react with the water inside clouds to give you this, which is aqueous in state, acidic, sulfuric acid. Okay? All three of these reactions are synthesis reaction happening one after another. This is actually acid rain. Okay? Sulfur is something that we put in our gasoline. Okay? So it makes it smell like gasoline. Gasoline actually is odorless. Okay? Which is troublesome, because if there's a leak and we can't identify it, oh no, there's GG all over the place. Okay, so that's why we put sulfur in gasoline. But without a good catalytic converter inside vehicle, you're going to be creating a lot of these guys. Okay? And when these guys decided to react with the water in clouds, that's how you make sulfuric acid coming down as acid rain. Okay, so these are, of course, synthesis reaction dealing with environmental factors. Okay, now I want to add some more. Okay, I'm an environmentalist. Everybody knows that, right? You guys are probably shaking your heads. Nitrogen gas. Okay, nitrogen gas also have the ability to create acid rain. How? Well, the first reaction is a synthesis reaction, where nitrogen gas react with the oxygen gas through combustion to give you nitrogen oxide. Okay? In fact, you get two of them. This nitrous oxide, what they call it, okay, will react with more oxygen gas, but only in the presence of a catalyst known as platinum, where you get nitrogen dioxide. Okay? Again, a synthesis reaction that I want you to sort of memorize. Now, this is where the bad part comes, but this is not a synthesis reaction though. Okay, you can see that it's not a synthesis reaction because you don't get two become one. Because with three of these nitrogen dioxide, when these guys react with the water in clouds, what you're going to get is that you're going to get a couple of nitric acid plus nitrous oxide. Okay, this, like this, will come down as acid rain. Okay, so nitrogen in our atmosphere, creating nitrous oxide is actually not a good thing at all. Okay, but of course, well, as I mentioned, the third reaction right here is not a synthesis reaction. Okay, so just something that I want you guys to know, because we all care about our environment. Anyway, that is synthesis. And the next day, we'll talk about decomposition. Okay, that's this one. This is kind of like the opposite of synthesis. And combustion. So we'll do combustion and decomposition together tomorrow. But hopefully you guys understand the complexity of synthesis and you understand how to balance these chemical reactions, because they are extremely, extremely important moving forward. Anyway, I'm gonna be quiet now, and I'll see you tomorrow. Bye, guys.